everyone, welcome to this live demonstration of QUAlibrate, quantum machine software for the automatic calibration of multi-qubit systems. We start at the core, which is the IDE, Visual Studio Code in this case. On the left-hand side, we have all the different calibrations for superconducting qubits of different types, and we're expanding this to different qubits. Some of these are for single qubits, others are for multi-qubit calibrations. In this case, let's look at a typical one, qubit spectroscopy. Now, we typically start with a description of the calibration, saying what it does, what it changes, and what happens. The next step is that we define our calibration node. This is a part of QUAlibrate, and all it needs is a name and some parameters. Now, another important point here is that we load our QUAM state. This state is a digital representation of your entire quantum system, so it contains all the information about your qubits, including the pulses, the properties, the connectivity, everything. We next separate our calibration node into different sections. We call these node actions. They're symbolized by these add_node.run action decorators. If we look at the first one, which is to create a QUA program, you see that there is code in here to create a QUA program that's sent to our OPX hardware to be executed on a QPU. So typically this involves pulse level. This uses our pulse level language QUA, and so it can include things like performing an operation, updating a frequency, and performing a readout on a resonator in this case. Now, so each of these different steps performs an action of this calibration node. For instance, another one is how to execute a QUA program, how to load data, how to analyze data in this case, plotting data, and one important step is performing updates on your QUAM state. So based on the measurement results, if it's successful, it will propose updates to your QUAM state. So for example here, it will propose to update your qubit frequency. And then finally, you can save your results based on here. So each of these scripts is a different calibration node, and you can run these through the IDE, and this is perfect if you're in sort of a development mode where you want to quickly run an action, look at the results, based on that make some changes. But once you reach the stage where you're comfortable, where your node is sort of fixed, and you notice you're only really changing the parameters, then it makes sense to switch to the QUAlibrate front end. So now we're at the QUAlibrate web app, more specifically the calibration node page. Here you can see each of the qubit calibrations that we've previously seen through the IDE, some of them for single qubits and others are for 2-qubit calibrations. In this case, let's look at the one we looked at in the IDE, qubit spectroscopy. You can see all of the different parameters that we've defined over there. You can change them if you want, or you can just hit run. So we're running this at the IQC where we have a superconducting QPU cold, and what we're doing here is in parallel over to the 2 qubits, sweep the RF frequency to try to find the qubit's resonance frequency. And if we look here at the results, we see that we're successful. In both of the cases, we see a clear peak, and more importantly, the fit was also successful. Based on that, it predicts a new RF frequency for your QUAM state. Things look good, so let's hit accept. So this updates your QUAM state with the updated values. Now, let's look at another one, Power Rabi in this case. In this case, we perform a pi pulse but vary the amplitude. This allows us to extract a rough estimate of the required pi pulse amplitude for our qubits. Looks good, we see a clear maximum and the fits were successful, so it again predicts values. Let's hit accept all. And now we have a roughly calibrated system, so let's look at how we're doing. We turn to our standard metric of randomized benchmarking, where we perform a large number of Clifford operations and a final inverting Clifford. Ideally, this brings each of the qubits back to the ground state, but due to decoherence, it will become increasingly unlikely as the number of Clifford gates increases. So here we see the randomized benchmarking results, and we see that as the Clifford length increases, the system decoheres more and more. The fidelities are around 99%, which is not bad, but it's not great. Not surprising, because we've only done a very rough calibration. To boost these fidelities, we really need to turn to an automated calibration graph. So if we go to our graph library, we now see 2 types of calibrations. First, we have a fine retuning graph. This is only if you're a little bit off the tuning point. In this case, there might be more serious things wrong, so let's go to the full graph. This has 13 calibrations, each of which you can change the parameters if you like, or if you're happy with it, let's just hit run. So this is again performing the entire graph in parallel on all of the qubits. You can zoom into specific steps. So for instance here, the first one is resonator spectroscopy. And we see that we find the resonance frequency of each of the two resonators. So this whole graph works on a QPU where you only very roughly know the values. For instance, if you know the specs given by the QPU provider, and it iteratively tunes up your entire quantum system. So you're going through the different steps. Here we have our qubit spectroscopy. Again, the QUAM updates are automatically accepted if the fit is successful. And then we go to the next measurement. So here we are performing qubit spectroscopy as a function of flux. So this allows us to find the sweet spot of our qubit. We then go to our power Rabi measurement to get a rough estimate of our pi pulse amplitude. And you can go to previous measurements if you want. So here we go to the previous one. We can go to the latest one, which is Ramsey. So this very accurately finds your resonance frequency for each of the two qubits. All of this is being done in parallel on the qubits. So it scales very well with the number of qubits. Here we're finding the the optimal readout point for each of the qubits. And based on that, we can find the correct readout threshold. And we get a readout fidelity of about 90%. Now we then do Ramsey on the qubits as a function of flux to find both the sweet spot and the frequency accurately. And now we're slowly approaching the end of our calibration graph. We're now doing a drag calibration to find the drag coefficient, which is required for really high fidelity single qubit gates. Right? The final two steps before we do the validation is to very accurately determine the pi pulse amplitudes and the pi half amplitudes for our qubit. So here we do a pi pulse amplification, so we're performing up to 200 pi pulses consecutively. This allows us to find a very accurate estimate of our pi pulse amplitude. We're then also doing the same for our pi half amplitude. And as you can see, we've already done quite a few calibrations. You can look up at each of them as you go along. And so in this case, we did the pi half amplitude, which is the latest one here. So we're performing consecutive pi half pulses to again find the correct amplitude very accurately. And finally, we perform randomized benchmarking. As you can see, the fidelities have improved quite a lot, reaching above 3 nines. And all of this is fully automated, fully parallelized, and all in just over 2 minutes. Finally, you can look at the data of the latest measurement, including the QUAM state and any updates. So for instance, if we go to the Rabi amplitude, you can see that the pi pulse amplitude has been changed slightly based on this measurement. You can also see all of the information about your qubit state at the end of this measurement. And you can go back all the way in time if you like. Thank you very much.